Okay, this is our third lesson in Unit 8, accumulation functions related to real world or applied situations. You know, earlier we said that if you want an amount, you need to integrate a rate. And we've integrated velocity to find out amounts. Now we're going to see how accumulation or net change problems give us scenarios where we can calculate the value of some quantity over time. Here's our first example. Let's say you got a 10-week-old Basset Hound puppy for your birthday, and you discovered he's gaining weight at this rate e to the 0.0125 pounds per week, and t is the puppy's age in weeks. At 10 weeks, the puppy initially weighed 14 pounds, so that's our initial condition. And we want to know what the expected weight of your new puppy is at the end of 15 weeks. So we would want to integrate the accumulation over that 5-week period. So the initial plus the accumulated weight gain would give the total weight at the end of the 15 weeks. If we start off with 14 pounds and we add that integrated amount from 10 to 15 of our rate equation, we can let the calculator do that for us. So jumping over to that screen, I put the function into, oh, that's not quite right, is it? Oh, so the calculator just rounded it into the calculator, got the graph of that, jumped over to the calculator screen. From 10 to 15 weeks is 5.84654. So 14 plus 5.84654 gives us a total weight at the end of that 15th week as 19.846 pounds for our new Basset Hound puppy. Okay, on to the next example. In example 2, an electric monorail transport is slowing down at a rate of 2t plus 25 feet per second. So this is by the units, that's our acceleration. And t is the time in seconds. By how many feet per second? Whoa, something happened there. By how many feet per second does the monorail slow down between 1 and 5 seconds? So we could calculate that between 1 and 5 seconds for that rate. 2t plus 25 dt would give us t squared plus 25t on the interval from 1 to 5. So 5 squared, that's 25, plus 25 times 5, 125, minus 1 plus 25. So what you got? 150, excuse me, minus 26 is 124 feet per second that the electric monorail was slowing down. So we integrated acceleration to find velocity, which was the rate that the monorail was slowing. The number of liters of oil in a tank is changing at this rate, 0.26 liters per minute. T is the time in minutes. Initially, the tank contained 14 liters of oil. Write an expression that can be used to find the amount of oil in the tank after 10 minutes. So this is just an example of translating a verbal expression into an algebraic expression. So again, we want the initial amount plus the accumulated amount from 0 to 10 minutes, integrating the rate equation. And there's our expression if we wanted to actually calculate it. would end up with 14 plus 1300ths t squared from 0 to 10, and that would be 14 and 13 minus 0, so that would be 27 liters in all if you wanted to calculate it. But this is all they were asking for in the example. Example 4, describe the meaning of each expression in the context to the given scenario. So the function WT gives the number of water bottles produced by a manufacturer by time t in hours on any given day, and we want to explain the meaning of that expression. So you can see that we've got from 4 to 8 is our interval, and that would be in hours. So this expression would be the number of water bottles produced. Number of water bottles produced by the manufacturer during the 4th through 8th hours. The next one, part B, the amount of oil being drained from your pickup truck is decreasing at a rate R of t quarts per minute, where t is the time in minutes. What does the expression mean? The antiderivative from 3 to 4 for the rate is -1/2. So this is telling us from 3 to 4, that's during that 4th minute. During the 4th minute, the amount of oil drained from the truck, it's negative, so the amount of oil that drained from the truck decreased by 1/2 quart. Whoop. Got to put the time in there. During the 4th minute, the amount of oil that drained from your truck decreased by 1/2 quart, 1/2 quart. On part C, Kevin got a gift certificate, got a gift of $500 from his grandparents for graduation. He deposited the gift into his college savings account. Smart boy. And Kevin's savings grows at a rate of R of t, hundreds of dollars each month. T is the month of the year. What does the expression below mean? Well, let's see. We're going from, looks like from the 1st month to the 12th month. So by the end of the 12th month, Kevin's account had a total of $2,400 in the account, because he started off with $500. So we could put that into words: by the end of the 12th month, Kevin's account had a total of $2,400 in the account. Okay. Next one, example 5. So table problems, those are always really popular. A city bus is accelerating from 0 to 18 seconds. The data for the acceleration is recorded in the table below. If the velocity at time 0 is 6 feet per second, find the approximate velocity at time equals 18 using a trapezoidal sum. So put that together in a sentence. The velocity at 18 is the initial amount plus the area accumulated on the table from 0 to 18 of the acceleration function. And we're told to use a trapezoidal sum. So we have initial amount of 6, and let's see, you notice that these intervals, they're all 3 seconds apart. 12, 15. So we could say, in general, a trapezoid is half of the width of the interval, and then we're going to add the sum of the bases. So for the 2 endpoints, we just have that first value once, but we've got 2 4s, 2 6s, 2 8s, and so on and so forth, because they're on the interior part of the trapezoids. 2 6s, 2 8s, 2 7s, 2 9s, and 1 10, which turns out to be 6 plus 3 halves. And somebody check me with the calculator. I believe that adds up to 79. So the total would be 124.5 feet per second is the approximate velocity at 18 seconds using the trapezoidal rule. So we can convert verbal expressions to algebraic expressions. We can integrate and accumulate with initial conditions. And we can use a table to accumulate. We can use a graph to accumulate. So the graph at the right shows the rate in gallons per hour at which storm water is being pumped from an overflowing canal. We want to find the approximate number of gallons pumped from the canal in the 24-hour period. So roughly the easiest thing to do would be to use a right Riemann sum or a trapezoidal sum. Let's see. So this, oh, I can't get it to color. Yeah, not coloring very well. See if we can get a, there. So from here to here, and then get a different color from here to here. And then the third trapezoid. Fourth trapezoid. Go back to yellow. Where are we going to stop? In the 24-hour period. And then one more green. Okay, so we've got to calculate the areas for each one of those trapezoids. So the gallons of stormwater can be estimated over that 24-hour period by integrating the rate. See, they're telling us this is a rate, checking the units on the x and the y-axis. So that's roughly, using the trapezoid rule, each interval is 4, so half of 4 times the sum of the bases. So this first base is 100, and that second base is 125. So I've got 1 100 and 2 125s, because that height right there is shared by the yellow rectangle, or the yellow trapezoid, and the green trapezoid. And then we've got 2 more. So let's just make an estimate of that one. Maybe that's 135. Looks like it's somewhere in there. So 2 at 135. And then this one here, we'll call that at 130 possibly. Just kind of ballparking that because it's an estimate. And then this one at 16, let's call that height about 110. So 2 at 110. And this one at 20, we'll call that one 85. So 2 at 85. And the last one, roughly 65, plus 65. So we got 2 times the sum of all of those. Check me on the calculator, make sure I'm not doing anything too crazy. 2,670 gallons of storm water that they pumped out of this retention pond or overflowing canal. It was an overflowing canal. Okay, so we can accumulate with a table, and then we can accumulate with some functions. This one's related to marginal cost. So find the cost to produce 50 widgets if the initial cost is $1,800 and the derivative or the rate is 155 minus 30 x plus x squared. Let x be the number of widgets produced. Let's see if x be the cost to produce the widgets. C prime of x is called the marginal cost. So let's label this. This is marginal cost. That's the cost to produce one additional widget if you're currently making x of those widgets. So the 50 widgets would be C of 50 minus C of 0, which is the accumulation on that derivative. So from 0 to 50 of 155 minus 30x plus x squared dx. We'll do this with the calculator here in a minute. Is 155x minus 15x squared plus 1/3 x cubed over that interval. And that's 155 times 50 minus 15 times 50 squared plus 50 cubed over 3, and then plugging in 0, all of that's gone. So jump to the calculator. I had 6.66 repeating. And then back to the problem initially so we can get our brain wrapped around this. We want to know the C of 50, the cost to produce 50, but there's an initial cost of $1,800. So we've got the cost to produce that one extra plus the initial cost, which was $1,800 plus the marginal cost, 916.67. So our total cost is the sum of those. For producing 50 widgets is $13,716.67. Okay, so 8.3. Next time, area under a curve, or area between two curves.